Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on group, lecture number 69, in which I will discuss on P-Sylow Subgroup and Shallow's Theorem. Now we wish to know what is P-Sylow Subgroup. Let G be a finite group of order P to the power m multiply n. P is a prime number and P does not divide n. Then if there exists a subgroup H of G of order P to the power m, then the subgroup H is called P-Sylow Subgroup of group G. Now we write the definition of P-Sylow Subgroup. Let G is a finite group and order of G equal to P to the power m multiply n, where P is a prime number and P is not divisor of n. Then a subgroup H of group G is said to be a P-Sylow subgroup of group G if and only if order of H equal to P to the power m. Now we state and prove Shallow's theorem. Statement: let G is a group of finite order and P is a prime number if P to the power m divides order of G and P to the power m plus 1 is not divisor of order of G, then G has a subgroup of order P to the power m. Now we prove this. Given that G is a finite group and P is a prime number, also given that P to the power m divides order of G and P to the power m plus 1 does not divide order of G. Let this is number 1, this is number 2. We have to show that G has a subgroup of order P to the power m. We shall prove the theorem by method of induction on order of group G. We shall prove the theorem by method of induction on order of group G. Let m equal to 0 implies that P to the power m equal to P to the power 0 equal to 1. Let this is number 3. Let order of G equal to 1. Let this is number 4. Since 1 divides 1 implies that this 1 is P to the power M. Divides this 1 is order of G. This is number 5. Since P is a prime number, therefore P belongs to the set containing elements 2, 3, 5, 7, ... Therefore P does not divide 1. This P may be written as P to the power 0 plus 1. Does not divide 1. Implies that P to the power 0 means M plus 1. Does not divide. 1 means order of G. This is number 6. Therefore, for order of group G equal to 1, P to the power M divides order of G, and P to the power M plus 1 does not divide order of G. Then we have a subgroup G of group G. With order 1 equal to P to the power M. Therefore, the theorem is true. For order of G equal to 1. Let theorem is true for groups of order less than order of group G. Let this is number 7. Now let M greater than 1 and given that P to the power M divides order of G, implies that order of G equal to P to the power M multiply N. N is an integer. Let this is number 8. Also given that P to the power M plus 1 does not divide order of G, implies that P to the power M multiply P does not divide order of G is P to the power M multiply N, implies that P does not divide N. This is number 9. From 8, we get that G is a group composite order. Since order of G is equal to P to the power m multiply n, this is a composite number. Therefore, G must have a subgroup H. Let order of G by order of H equal to Q implies that order of G equal to Q multiply order of H, implies that order of G is P to the power m multiply n equal to Q multiply order of H. Let this is number 10. In 10, if P does not divide Q, then P to the power m divides order of H. This is number 11. Since P to the power m plus 1 cannot divide order of H, because H is a subgroup of G, if P to the power m plus 1 divides order of H, then P to the power m plus 1 will divide order of G. So, P to the power m plus 1 cannot divide order of H. Hence, we get that H is a subgroup of group G such that order of H less than order of G. P to the power m divides order of H, and P to the power m plus 1 does not divide order of H. Therefore, by using 7, in 7 we have, if any group whose order is less than the order of G and P to the power m divides order of that group, also P to the power m plus 1 does not divide order of that group, then there exists a subgroup K of H such that order of K equal to P to the power m. Since K is a subgroup of H and H is a subgroup of G, Therefore, K is a subgroup of G of order P to the power M. Therefore, in this case, theorem is true. Now, in 10, if P divides Q, that is P divides order of G by order of H. Let this is number 12. Let Z be the center of the group G. And let A does not belong to Z. And NA be the normalizer of element A of group G. Since normalizer of an element of a group is a subgroup. Therefore, NA is a subgroup of G. Let H equal to NA. Therefore, from 12, we get P divides order of G by order of NA, implies that P divides sum of A does not belong to center of group Z. Order of G by order of NA. Let this is number 13, this is number 14. From 13, order of G by order of NA equal to Pk. K is an integer, implies that order of G equal to Pk order of Na. Implies that P divides order of G. Let this is number 15. The class equation is written as order of G equal to order of Z. Z be the center of the group plus sigma A does not belong to Z order of G by order of Na. This is number 16. From 14, 15 and 16 we get here P divides order of G in 15. In 14, P divides sigma of A does not belong to Z order of G by order of Na. Therefore, P divides order of Z. This is number 17. Since Z is an abelian group, therefore, from 17, here in 17, P is a prime number and P divides order of Z, then from 17, by using Cauchy's theorem, for abelian group, B belongs to Z such that B to the power P equal to identity element. Let N is a set containing elements B, B square dot 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 B to the power P equal to identity element. Let this is number 18. Since N is a cyclic group, therefore N is a normal subgroup of G, implies that G by N quotient group, G by N exists. Let quotient group G by N equal to G prime. Let this is number 19. Now, order of G prime equal to order of G by order of N. Order of G is P to the power M multiply N, and order of N equal to P, and this equal to P to the power M minus 1 into N. This is number 20. Here we see that P to the power M minus 1 divides order of G prime. Since P does not divide N, implies that P to the power M minus 1 multiply P does not divide order of G prime, implies that P to the power M minus 1 plus 1 does not divide order of G prime implies that P to the power M does not divide order of G prime. This is number 21 and this is number 22. It is obvious that order of G prime is less than order of G. Also, P to the power M minus 1 divides order of G prime and P to the power M minus 1 plus 1 does not divide order of G prime, and we have assumed that the theorem is true for groups of order less than G. This is number 23. Therefore, from 23 we get G prime contains a subgroup S prime of order P to the power M minus 1, that is order of S prime equal to P to the power M minus 1. This is number 24. Let phi be a mapping defined on G into quotient group G by N, defined as phi x equal to xn. Therefore, phi is a natural homomorphism. That is, phi is onto homomorphism with kernel phi equal to n. This is number 25 and this is number 26. Let S is a set containing all those elements of group G such that phi x belongs to S prime. Now we shall show that S is a subgroup of G. This is 27. Let x, y belong to S implies that phi x, phi y belong to S prime. Here, if x belongs to S, then phi x belongs to S prime. And S prime is a subgroup of G prime implies that phi x, phi y whole inverse belongs to S prime, implies that phi x, since phi be the homomorphism, therefore this equal to phi y inverse belongs to S prime, implies that since phi is a homomorphism, implies that phi x y inverse belongs to S prime, since phi is a homomorphism, implies that x y inverse belongs to S. If phi x belongs to S prime, then x belongs to S. Therefore, we get x y belong to S implies that x y inverse belongs to S. Hence, S is a subgroup of G. This is number 28. Since N be the identity element of G by N, quotient group G by N, that is G prime, and N equal to kernel of phi. Therefore, if x belongs to kernel of phi, implies that phi x equal to N, identity element of G by N, quotient group G by N, that is G prime, implies that x belongs to N, implies that phi x equal to N. This is number 29. Since S prime is a subgroup of G by N, quotient group G by N, that is G prime, therefore S prime contains identity element of G prime. Therefore, N belongs to S prime. This is 30. From 29 and 30, we get x belongs to N, implies that phi x equal to N belongs to S prime, implies that x belongs to S. Therefore, N is a subset of S. This is 31. Since car phi, kernel of phi equal to N, implies that N is a normal subgroup of group G from 31, we get that N is a normal subgroup of S. Therefore, quotient group S by N exists. Since phi G to G prime is onto homomorphism, therefore it induces that phi S to S prime is onto homomorphism. This is S and this is S prime. This is phi is a onto homomorphism. Since kernel of phi equal to n and phi S to S prime is onto homomorphism. Therefore, from first isomorphism theorem, here this is n equal to car phi, kernel of phi, we get S by N is isomorphic to S prime. This is psi isomorphism. Isomorphic to S prime. This is number 32. Therefore, order of S prime equal to order of quotient group S by N. This equal to order of S by order of N implies that order of S equal to order of S prime multiply order of N. Order of S prime is P to the power M minus 1 and order of N is P. This equal to P to the power M. This is 33. Therefore, S is a subgroup of G with order of S equal to P to the power M. Therefore, theorem is true. In this case, hence G contains a subgroup of order P to the power M. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.